Well, good morning, good afternoon, good evening, wherever you are around the world. I'm Bill Ragsdale, the founding president of the Fourth Interest Group, and wrote the Fig Fourth model from back in the Stone Ages of Fourth. Today, we're going to carry on a theme that I started 1 month ago. We discussed the bubble sort then. Today, we're going to investigate the insertion sort. So last month, bubble sort. It's a quick to implement, fairly simple sort, however, quite inefficient from a time standpoint. The number of passes through the file is n squared, so increasing the number of rows dramatically increases the execution time. Today, we're going to investigate the merge sort. In this case, it's much more time efficient. The execution time is in proportion to the number of rows times the log to the base 2 of the number of rows. Jumping to our conclusion today, here's the result we're going to see. The time for execution for the 10-row version of the bubble sort is the same as the merge sort, less than 1 millisecond, less than I can measure. For 100 rows, the bubble sort takes 20 to 30 milliseconds. And look, the merge sort only takes 2 to 4 milliseconds. It even gets better at 1,000 rows. The bubble sort takes between 2 and 4 seconds. The merge sort is down still in the millisecond range, 15 to 16 milliseconds. A proof in the pudding is the 10,000 row sort. That took for the bubble sort between 5 and 7 minutes. And for a merge sort, it's less than 2/10 of a second. About the time of a keystroke or two, so the sort time would be hardly noticeable. So let's look at how the merge sort operates in summary. The key is locating runs. A run is defined as a monotonically increasing series of values. So when you have a series of values increasing and then a following value occurs that is smaller, that terminates the run. In this case, we're using a matrix for our operational field. And along the columns of the matrix, there certainly would be a large number of runs which are isolated and merged together until we have finally one long sorted matrix. The method starts out by locating a pair of runs at the leading edge of the matrix. We merge sort that pair, forming one run. If an odd run is at the matrix end, then it is just carried across. Now we repeat until 2 runs remain. So we sort pairs down to increasingly longer runs and a smaller number of the runs. And of course, this goes by powers of 2, as we will see. The final case, when we only have 2 runs remaining that occupy the entire matrix, one final merge sort pass combines them all into a single value, a single run, and now we're done. The work starts with a word call scanner, fourth word call scanner. The curly brace at the beginning indicates that it operates on the matrix and it has to receive the address of a matrix and control parameters. So the first thing we do in this routine is we have to set the termination value as a default. So the row number of the last matrix row is set as a default termination. In this matrix system, the rows run from 0 to n minus 1, where n is the number of rows. So we set that n minus 1 value as our exit value. Now the scanner begins at a starting row which is specified. Its value is compared to the following row, immediately following row. And upon finding the row with a less or equal value, we return the row number. So if we find a greater value at a following row, that terminates this particular run. If the values continue to increase, the scan is continued until it does find a decreasing value. And if no ending value qualifies, the word has run completely to the end of the file. So again, it returns the default value, which is the last row in the matrix. This is the code for scanner. We see its input parameters. The X curly brace is the address of the matrix we're operating on. R1 is the row at which the scanner begins, and C is the number of the column that is used for comparison. We are sorting on the column C. The first row at n prime 1 minus 2 result, that sets the ending value. So result is our default final value. The 3 dupe with a curly brace at fetches the floating point number, which is in the origin row. The n prime 1 minus row sets up the do loop parameters. Now, on a sequential basis, the do loop scans ahead row by row by row. The 2 dupe I1 plus swap curly brace at fetches the target row comparison value. The F dupe, F rote, and F less than determines which row, if the second row has a lesser value. If the second row has a lesser value, then I is the I value, which is the upper row value, is placed into result, and the process leaves to resume execution after the loop. So this do loop will continue chugging along until it finds a declining value. It returns the row number of that declining of the row above the declining value. It will return the last row of the run. If we get clear to the end, the 2 drop and F drop do a little cleanup of the stacks. Result returns either the I value or the default value. And at the end, a comparison is made. The n prime 1 minus equals determines if we're at the end of a run or not. So the 2 parameters that are returned is number 1, the last row of a run, and then a flag indicating was that at the end of the matrix or not. There are determining the last row in the matrix is very important because this is this indication that a particular scan has been done all the way through the end of the matrix and it's time to restart. So the word run locator, again with the curly braces, indicates that it accepts a matrix location as an input. It uses that previous word, the curly brace scanner, to find a run. Upon finding a run, which is guaranteed in this case, it now then sets the value of A prime to the address or the run number of the first row, and it sets AX prime to the last, the row number of ending the run. So the first job is to locate the first run, and then it would return a particular code if there is no following run. So AX will hold the value of the ending row, and a return code signifies that. If a second run is found, however, then B prime is set to the start of the second run, and BX prime is set to the end of the run, and then there is a return code. So at this point, we know we either have 1 run or 2 runs, and we've identified the start of the first run if it's there, and the location of the second run if it's there. And the code to make this happen. The curly brace locator, as you see, it accepts X brace, which is the address of the matrix. The row is the row at which the process is started to analyze 2 runs, and again, C is the column on which we are sorting. The first row that begins over 2 A prime initializes those values of A, AX, B, and BX. The next one checks to see if A prime is 0. If this is the case, we are at the very start of the matrix, and therefore we have to initialize the pointer to our output file or output matrix. The output matrix uh, row counter is W row. So as information is added to the output matrix, W row increments, always pointing to the next available empty row in the output matrix. So 3dup duplicates the input parameters and applies the scanner. And the scanner always identifies AX prime, which is the ending the ending row, and the flag that was returned is tested to see are we at the matrix end. If we are at the matrix end, there has only been one row found, and so the value of 0 will be placed on the stack and exit is made. On the other hand, if there is a second end run, then the AX1 plus to B prime starts the beginning of the second scan. So the second scan begins in the row after the end of the first row. Scanner runs, and again, it sets up it completes the B and BX values. Then at the final end, the returning flag is returned. Remember, it can be at this point either a -1 or a +1, indicating we are or are not at the end of a run. ToMerge starts to do the real work. It uses locator to determine the locations of 2 runs. Knowing those 2 runs are present, ToMerge will then merge those 2 runs into a single run in the working output file. The first step it does is to find the row with the smallest C value. Remember, this is it's examining 2 runs, and it looks at the initial value or the initial row of those 2 runs, picks the one with the smallest C value, and it copies that identified row into the working matrix. So we have now passed the lowest valued row goes to the working matrix. And we test to see if the run has been exhausted. Now, it might have been that the run only had one row in it. If it has been exhausted, then the remaining row, the other half, is automatically known to be in sorted numerical order because it is a run, and so that the other run is transferred to the working output. So whichever run has been exhausted, the mirror opposite row run goes to the working matrix. And upon that case, the next start row is set into A prime. So in this case, we have either sequentially gone through the 2 runs, finding the smallest. We have moved the terminating other run into the working file, working matrix, and now the whole process restarts. This is the code. Notice it's in one big begin again loop. So this will operate sequentially until it reaches the end of the matrix. We can't use a do loop here because we don't really know how many rows remain in the matrix, but the begin again indefinite loop will scan until it finds the end of the matrix. The first row pair, the dupe A prime swap bracket bracket fetch, gets the first cell value. The second sequence gets the second cell value, and a comparison is made between the two. If we now know the row that needs to be transferred, so the over A prime 0 bracket bracket gives us the address of the origin row, and then working W row 0 bracket bracket gives us the address of the destination in the working matrix, and then X byte C move moves it over. We have moved the entire row. Rather than doing a column by column move, we identify the address of the entire row, and it moves in one step. At that point now we increment because we're moving ahead. So A prime is incremented by 1. The W row is incremented by 1. And now we look for is the row has the row been fully transferred? The A prime AX prime comparison tells us that yes, the leading row, the A run has been fully transferred. So in this case, we then copy the second run across. On the other hand, if at the beginning we realize that we're processing the B row, this the else over B prime 0 bracket bracket identifies the row of the second run, the working W row 0 bracket bracket, and followed by a C move moves that row to the working matrix. And now a test is made to see, is this row exhausted? And if it is, we now copy the first run. So we see here, this is the nuts and bolts of the merge sort. This is picking out the row with the smallest value, moving it to the output, and it's checking to see, is that process ready for completion? There are 5 different situations that need to be addressed. As we are doing this merge, there are 5 conditions under which it can take place. The first is that in scanning the matrix, one run is found from beginning to end. The run originates at row 0 and it ends at row n minus 1. Therefore, the matrix is already sorted and we are done. The next case is that if 2 runs are found, the leading run begins at row 0 and the second run ends at n minus 1 at the end of the matrix. In this case, there is only one merge necessary, so we do one merge and then exit, and we are completed. It also could be that 2 ending runs are found. In other words, we find 2 runs, they end the matrix, and in this case, we merge the 2 together, but we know there is more sorting to be done, so the entire process is restarted. Along comes E, the E case. We find 2 runs. They are not at the end of the matrix, so we just merge the 2 runs together and continue ahead. This is where the work is done. Almost all execution is at E because we find 2 runs and merge, find 2 runs and merge, find 2 runs and merge, and continue. Finally, when we get down to the end of the matrix, we hit case D. 2 ending runs are found, so they are merged, and now we start the sort restart. We restart the sort. So again, most of the action is E followed by a D, which gets us the restart. And then the ultimate end is on C. When only 2 runs are found, we do that one merge and we exit. Now there's one more case that's a little odd one, and that is if after going all the way to the end of the matrix, only one ending run is found. That's one run found at the end. There is no mate run to pair it with. So it is just carried across into the working output. And then the restart is again. So in this case, that one last little row is known to be sorted, but there's nothing to pair it with, so it is carried across to be handled in the future. And we'll talk about this in a moment. So this is the final routine. The M sort handles the matrix sort. In it, we initialize the parameters A, AX, B, and BX. Run locator, which sets up those particular values. It will preload either of these values based on the 1 or 2 matrices that are found. This is passed to a case statement, and within the case statement, we now take one of those paths that we just mentioned from A through E. The first selection is tested is the E case, which is the most likely. Again, this is the one that sorts sequentially through all the rens. If the E case is not taken, the AB case or the CD cases are taken. And these three routines will return a value to either repeat the sorting process or to end and exit. Here's the code. The starting point is we set up and run locator, and now that has set up the AX, B, BX routines, and has returned a value saying, do we have one or two runs available? The case executes, and it takes those values, either the 1, the 0, or the -1 that has been returned by the locator, and it selects either the case E, the case AB, or the case CD. A word handles each of those three cases, and within them, they are then applying the process that we mentioned just a moment ago for the 5 cases. And if none of these execute, then we get an error code. And because of the simplicity of this case should never happen, will never happen. And finally, the routine runs through the begin until a true value is returned, and that says sorting is complete. The 2-drop cleans up the stack, and we are done. To review those elements that are chosen by the case statement a moment ago, remember that a case is just one run matrix fully sorted, and we get an immediate exit. The C case, 2 runs are found. We do the one merge, and then we exit again. This is the D, and E are ongoing internal processes that repeat. For D, we have 2 ending runs. We merge them together. We know we're at the end of the matrix, so the job there is to restart, and the sort is resumed. And the E, remember, is the 2 runs that are merged and continuing through the entire matrix till the end. And finally, the B is that one case which has the ending run is found, is carried across and restart. So that ending run will be carried all the way through up until all of the upper runs have been merged together. And so we finally only have one big long run all the way down to the bottom with that one little short ending run carried across at the end. And then the final merge is done by C. We have 2 runs. We do the one merge and we exit. Oh, here's how it looks in real life. I've got a matrix that is 2 columns by 12 rows, and they're full of random number floats. These are integer values, but remember these are float values, so they can take any value, positive or negative. After doing the sort on column 2, notice that the column 2 is sorted running from 6 through 7, 8, 9, 13, 15, and down the bottom 17 and 19, all nicely in numerical order. If we then sort on column 2, now column 2 is placed in order, and it starts at 1 down to 2, 5, 7, 10, 16, 17, down through 19. Now, one of the desirable features desired in a sort is to have what's called a regular sort, and that means that when you sort on more than one value, the sub-sorted elements retain their corresponding order. And we see, yes, in this case, this sort is regular because we have sorted on row 2 and then sort on row 1. And so under the 5s, notice the 3 5s, the sub-sorted values are 9, 13, and 15 retained in order. And for 19, likewise, the second column retains its original order, which is 6, 17, and 19. So we'll review the performance information again. We see that for 100 rows, the 10 to 30 millisecond time frame has gone down into 1 to 4 milliseconds. The 1,000-row sequence ends up into a 15 to 16 millisecond time range, and this gigantic 10,000-row sort is done in much less than 2/10 of a second, somewhere in the range of 65 to 110. The variation on these, of course, is how random was the input and how many runs were in the original input. This is the reason that this sort is so efficient. We look at the number of passes that are made. A pass would be when the matrix is scanned from the first row to the last row. With a 10-row bubble sort, 50 passes are made. This is n squared over 2. The number of rows squared is 100, divided by 2 is 50, so 50 passes are made. In the merge sort, this is done on a power of 2, and so only 4 passes are done. For 100 rows, the bubble sort would do 5,000 passes. The merge sort does only 7. For a 1,000-row matrix, the bubble sort is now doing 500,000 passes through that matrix, and the merge is only doing 10. And the winner, of course, is the 10,000-row matrix. It has required 50 million passes by a bubble sort, and in the merge sort, it is just 17. Every time you double the number of rows in the matrix, you only add 1 to the merge sort because it's a power of 2. Remember, that's very important. Every time the number of rows doubles, you only add 1 more pass, not 20 million, 50 million, or whatever. So some discoveries. The one I mentioned earlier that says if we start with an odd number of runs, then you will always have a short run remaining at the end until the very last merge. That last odd run is carried across until the last sort. So this demands that last final merge to process that very last short run. So one solution for this is that if you make one pass through the entire matrix doing a merge sort and find that odd run at the end, then come back and do an in-place bubble sort on the first run pair. That first run pair is likely only to be 5 or 10 rows. Merge those first 2 runs together into one. Now we have an even number of runs, and we save that last odd run, and we reduce the number of runs by 1. The time sort will decrease by the log to the base 2 of n minus 1 over log to the base 2 of n. That is, imagine we are doing a 1,000-row sort, which would normally take 10 passes. This will reduce it from 10 passes to 9 passes. That's a 10% savings. So by doing this one little tweak of this bubble sort at the beginning, we've made a 10% improvement in time. The time saving is even more dramatic for a smaller number of rows. This works because we tend to keep all the runs of a similar size. So we're going to summarize here. This merge sort requires an identical added workspace for the sort values. So whatever the matrix size is we are working on, we have a secondary workspace of the same size. I do this by allocating a temporary RAM space in free space. So the burden is not present until the sort begins. When the sort begins, the temporary space is allocated. It is used throughout the sort, and at the end of the sort, that temporary space is released. The space needed for this extra storage space is the number of rows times the number of columns times 8 bytes. As an example, for a 1,000-row matrix by 5 columns, this would be 40 kilobytes. This is not terribly significant, say, running at a PC computer level, but it might be a problem if you're doing an embedded system on having that extra memory available. There are other sorts that use a smaller working space, and that certainly is worthy of research. So to wrap it all up, I will say that the bubble sort is compact. It's only 20 lines of code or so. So I'm going to leave it into my matrix code uh, base application, but I'll make the merge sort a load module. The merge sort came out to about 100, 110 lines of code, and I'll just make it an add-on module to bring when I need it. So here's what I found. The sorting and optimization can be an infinite time sink. You can spend as much time on this as you want. You can find new methods, new tweaks, little discoveries. I found 2 or 3 small changes to make along the way that made this improve a little bit better. But I think I'm done. I've had a great exploration. I've enjoyed doing it. I've learned a lot, and I've enhanced my matrix system. So I'd like to thank you all for your rapt attention, and now I'll return back to our fearless leader, Kevin. Thank you very much, and goodbye.